Hi, in this video I will discuss Hall effect, which is a part coming under magnetic fields. Hall effect is discovered by Edwin Hall in 1879, so names comes after him. And Hall effect is used in various applications and mostly in sensors such as keyboard switch, position sensing, monitoring and controlling the wheel speeds in anti-lock braking systems, regulating voltage in electrical systems, velocity selector in mass spectrometer, etc. Okay, and then before discussing the Hall effect, I would like to consider electric field and magnetic field perpendicular to each other. So I take here is my electric field, which is vertically downwards. Consider this is a uniform electric field, and I take the electric field intensity to be capital E. And the magnetic field, which is perpendicular to the electric field, so I consider that to be into the paper. So here's my magnetic field, and I take the magnetic flux density capital B. So in this field I consider a charged particle of charge simple q and mass simple m is moving with velocity v. So here is a charged particle. I consider a positive charge, and charge is let's say q, and the mass is m, is moving with speed v. So this is an instant at instant of this charge. Let's say that this is a snapshot of this moving charge. So we if a charge is in an electric field, we know it will experience the electric force. Since this is a positive charge, that will experience a force in this direction, and let's take that force to be Fe. Fe, and we know we can write an equation for Fe, that is force is equal charge times the electric field. And this charge particle is moving in the magnetic field as well, therefore it will experience a magnetic force. And I think I forgot to mention that I consider the motion of a charged particle is perpendicular to the both fields. Okay, now we know this charged particle will experience a magnetic force, and to find the direction of the force we have to use Fleming's left hand rule. I hope you all know Fleming's left hand rule, and if someone doesn't know, here it is. So if you take your thumb, pointing finger and middle finger of your left hand and arrange in three directions such that they are perpendicular to each other, and if you point the middle finger in the direction of the motion of a positive charge particle, and the pointing finger index finger in the direction of the magnetic field, then the direction of the force acting on the charge particle is given by the direction of the thumb. So here is my left hand, so I take middle finger and pointing the middle finger in the direction of the motion of charge particle. So this charge particle is moving this direction, so it's positively charged. This is direction of a positively charged particle. So actually you can say, in someone say it's a current, it's fine. Okay, so I can take this to be this direction, and the magnetic field is into the paper, therefore force acting on it will be vertically upwards. So the force acting on this charge particle is vertically upwards. I take this to be Fm, magnetic force, and we can write the force. We know that force is equal magnetic flux density times charge times the speed of the velocity of the particle. So now we can see this charged particle experience two forces, uh, electric force vertically downwards and the magnetic force vertically upwards. Okay, now let's discuss three cases under this. Okay, the first one, if the magnetic force is greater than the electric force. Okay, so if the magnetic force is greater than the electric force, then this charged particle will experience a net external force, unbalanced force in vertically upwards. Therefore it will accelerate upwards. Therefore it will deflect in such a path. And the next case, if the electric force is greater than the magnetic force, then similarly this charged particle will experience unbalanced force, net unbalanced force vertically downwards. Therefore it will accelerate downwards, so it will deflect in such a path. And the third case, where electric force and the magnetic force are equal, then there is no external force or unbalanced force acting on the charged particle. Therefore it will go in the straight path. So now let's move to Hall effect. Okay, for this I consider a conducting cube. Let's for example say a copper cube. And this is connected to a battery. Here's a switch. And let's say this wall cube is inside a magnetic field where the direction of the magnetic field is perpendicular to this surface. That means the magnetic field direction I can show indicate as like this. So here's a magnetic field. So this wall cube is inside the magnetic field. Okay, and still we can't see any effect because the switch is open, so no current in this circuit, no moving charges, therefore no any charges will experience a magnetic force or anything. Okay, so now once I put this switch, we know there is a current in this direction. Let's take that to be I. So current is this direction, means electrons are moving in this direction with speed of drift velocity. We take drift velocity Vd. So then electron in this coffer cube also start to move in this direction. You know, if you take a copper metal in a metal, for example, the iron core is like this, and there are free electrons. We say that electron cloud. So once you put this switch, what happens? There will be electric field in this direction, right? So I mark here the direction of the electric field is in this direction. So here electric field in this direction, then what happens? Electrons are negatively charged, they will experience force in this direction. So now every electron will experience a force in this direction. Similarly, there are so many electrons, but I consider one electrons to explain this. Okay, so I consider electron in this cube. So in this conducting cube I consider an electron. and due to this electric field it will experience a electric force in this direction. That means it will tends to move in this direction with drift velocity. We take drift velocity Vd. So let's take this is Vd. Okay, so now we have a moving charged particle, right? And this charged particle is inside this magnetic field which is perpendicular to the its motion. Therefore it will experience a magnetic force, and to find its direction we have to use left hand rule. Okay, since this is a negative charge we have to use the direction to be the other direction, because we want to always consider to this is for positive charges. So if negative charges move in this direction, mean we can consider positive charges move in this direction. So if you use the direction left hand rule, the direction is motion is this direction and the magnetic field is uh, into the paper perpendicular to its motion this direction. Therefore there will be a force acting on it will be vertically upwards. So this is a magnetic force. Let's take Fm. So there will be magnetic force acting on each and every electrons moving through this conducting cube. Okay, so what happens now, now there is magnetic force acting on vertically upwards. So due to this what happens, these electrons will deflect. We know vertically upwards there is a unbalanced force in vertical direction, that is vertically upwards. Therefore this electron will deflect and goes towards the top of this conducting cube. So each and every electrons will deflect towards up, and then what happens, these electrons will store in this top layer. So we can see here minus charge storage, that means electrons store in this layer. Okay, so this side is electrically negative, that means here this side will induce to be electrically positive. Due to this negative charges, this side is going to be induced electrically positive. So now we can see there is another electric field coming arise from the storing charges. That electric field is in vertically upwards. So this is a electric field coming due to this storing of charges. Okay, and let's take that electric field is as E something E naught. Okay, so now there will be electric field is produced due to storing of these charges. And if I consider another charge again, so due to this electric field, this electron will again experience a force in downward direction. So here the electric field is vertical upward. Since the electron is a negative charge, it will experience a force in downward direction, and let's take that force to be Fm, sorry, Fe, electrical force. Okay, and so at the beginning, so when I put the switch, thing happens gradually. First at the starting few electrons comes here and it increases gradually, and when it increases the E naught value also increases. Okay, so we can see at the beginning Fm is greater than Fe. Okay, at the beginning Fm, the magnetic force is greater than Fe, but with the time we can see the number of storing electrons in the top layer will increase, right? Therefore this electric field also increases. So we know that Fe is E times charge times the electric field E naught, right? If this E naught is increasing, then if Fe also increases. Therefore we can see with the time Fe is increases. So now we know this Fe is gradually increases with time. So at an instant when the we know this value is increases, so at an instant what happens, this electric forces becomes equal to this magnetic force. Okay, so when this happens, okay, this no longer this electrons will deflect, right? Because earlier it was deflecting because this at the initially at the beginning only Fm is there, and after this electron store there will be electric force and then Fe, but still Fm is greater than Fe, therefore the still electrons will deflect towards the upper layer. But once this value is reached to Fe value is reached to equal as Fm, these electrons no longer deflect because now force balance, therefore the electrons will go in the straight path. So there will be a corresponding value for E, this E naught, let's take that to be EH, the electric field corresponding to this particular value, where Fm is equal to Fe. We can take that EH whole electric field, and we are in general we are usually don't talk about whole electric field, but instead we talk about whole voltage, which is VH. So if the distance, this distance is simple, if this separation is D, we can write this whole voltage, the voltage difference VH is equal EH times D. Okay, VH is whole voltage is equal this electric field times this separation. Okay, so now we have Fm is equal Fe. Now I can write Fm is equal, we know magnetic flux density times the charge times the velocity of this electron, that's Vd, is equal Fe, electric field, charge times the electric field, that is this electric field. So here E cancels off, therefore I can write EH is equal B times Vd, and from this equation I can write EH is equal VH over D. So taking this and substituting here, we get VH over D is equal B times Vd. So I can write whole voltage is equal this separation times magnetic flux density times the drift velocity. So this is a very good way of finding the drift velocity of electrons in a conductor. For example, if you want to say you want to find the drift velocity, so you can find, if you know the magnetic flux density, you can measure this separation using a vernier caliper or something, and to find the whole voltage you can connect from the top and bottom voltmeter, and you can find the whole voltage. So this is a method of finding the drift velocity. Anyway, and next thing we know I is equal N A E V D, right? This equation you study in electricity in the beginning. So the current is equal number of charge per unit volume times cross sectional area times charge of the electrons times Vd. I get Vd as I over N A E. So I can substitute that here, then I get VH is equal B times D times B times D times Vd is I over N A E. So I can write VH is equal H is equal d I over n a e. Here a is cross sectional area, that means this cross sectional area here. So this is, if I know this this thickness, let's take that to be t. So I can write a is equal d times t. So in this equation I can write VH is equal b d I in of a, I this term d times, so d cancels off, therefore I get VH is equal bi over n T E. So this is another equation for whole voltage, and this one as well, and this one. Okay, I think that's all about whole voltage. So bye, have a good day.